I'm Vaidehi. I'm so excited because today I get to talk to you about binary, the language of computers. So what is binary anyways? Well, binary is a number system, and it turns out that number systems are things that we deal with every day. We deal with a number system called denary, which is the base 10 number system. And the reason it's called base 10 is because there are 10 digits that it involves, 0 through 9. As you might be able to guess, the binary number system uses just 2 digits, 0 and 1. Binary has a really interesting history. The number system that we know today, especially in the context of computers, was created by Gottfried Leibniz. But it actually dates back to the ancient Egyptians, who used a binary number system for multiplication and division. Binary is the language of computers. But why binary? Why zeros and ones for computers? Why not 0 through 9 or anything else? Well, when you start to look at how computers are actually crafted and what they look like under the hood, the binary number system starts to make a lot more sense. Computers at their lowest level of hardware use something called circuits, which are a type of switch in order to send electrical signals. And the circuits that are used inside of a computer actually map to the binary number system. Circuits are the things that handle the little bits of electricity that pass through them in order to indicate whether something is on or off. A transistor is a single circuit, and it handles the on-off switch for a single digit. In the modern-day computer, there are billions of circuits that handle the on-off switches, and that comprise the actual computers that we deal with every day. So let's think about not the billions of circuits that make up the computer, but just one of them. A single circuit handles 2 possible states, on or off. An on state means electricity is passing through the circuit, whereas an off state means electricity is not passing through the circuit. Another way of thinking about on and off is true and false. If we think about true as the switch is on and false as the switch is off, we can start to see that there's an obvious comparison between the 2 states. So if we have on and true and off and false, we can also kind of map this to binary. We can say that when a circuit is on, we can represent it as 1, versus when a circuit is off, we can represent it as 0. So the 0 and 1 limitation of the binary number system might seem limiting, but it's actually mapping perfectly to the 2 possible states of every single circuit within our computer. So when we talk about computers, we usually use terms like megabytes, kilobytes, gigabytes, but let's just break it down into a single byte and what we really mean when we say a byte of memory. Well, a byte of memory actually has a really important relationship to how binary works. A byte of memory contains 8 bits. So when we look at a single byte, we're actually looking at 8 bits or 8 binary digits. Each bit within a byte actually corresponds to a binary digit of 0 or 1. Bytes themselves are actually pretty cool. A single byte can contain 256 different permutations, which means a single byte can represent 256 different things. We'll talk more about this in a future episode, but hold on to that thought, because 256 and binary are really important in computing. So what does anything represented in binary look like? Well, let's take something simple like a number. So here we have the number 102. But how would the computer read this? What does 102 look like in binary? Well, when we convert 102 into binary, it reads as 011001110. Remember that in base 2, in binary, each of these digits is called a bit, a binary digit, and this whole representation of the number 102 is actually 1 byte of information. So we can see that 1 byte of information is needed in order to represent the concept or the idea of 102. So what does 1 character look like in binary versus a page of text versus even a low-resolution image? Well, let's see what they look like to us and how that converts down into bytes and bits for our computer to read. We can see that 1 single character is represented by 1 byte, or 8 bits, which makes sense since we just saw that the number 102 can be represented in a single byte. But in order to represent a page of text, we actually need approximately 8,192 bits, or 1,024 bytes, which is the same as 1 kilobyte. Again, this is just an approximation. And what about a low-quality image? Well, you could use maybe about 1 megabyte to represent even a low-quality image. So 1 megabyte would actually be the same as 1,024 kilobytes, which is the same as 1,048,576 bytes, which is the same as 8,388,608 bits, which is a lot of bits. So as you can see, we think about things in terms of kilobytes and megabytes, but when you break it down, you can see that all of these sets of data can be transformed into just the bytes that they are, and even just bits that they are. And it's important to understand a little bit about how these bits work and how they work in the context of binary, since binary is the number system that fuels everything that we do with computers, even if we don't have to think about it most of the time. To learn more about binary, head over to Dev2, create an account, and follow me at Vaidehi Joshi. You can also stay tuned for more videos. Thanks for watching.
Thanks to Heroku for sponsoring BaseCS. I'm Ben, one of the founders of Dev, and I want to give a shout out to Heroku, the platform that's allowed us to scale from 0 to millions of monthly visitors since we started this venture a few years ago. We rely on Heroku's managed Postgres alongside the rest of their infrastructure to ensure reliability and flexibility as we scale. If you're looking to scale a complex web app without all the chaos, please check out Heroku. Thanks a lot.